Hello everyone, it's the disembodied voice of your once and future stats teacher. And let's look at this problem that when I first saw it took me forever. I was like, what on earth is happening here? And then you break it down and it's actually not that bad. I promise it's actually not that bad. But you have to keep your mind really organized, which means you probably need to keep the things that you're writing down very organized. And so, of course, if you were on the AP exam, you'd have a big blank piece of paper to write as much as you could. And luckily, I have explained everything and this sort of infinite whiteboard to do just that. And I can zoom in and out as I need to. So we look at this. I'm assuming you've read this already. And we have these people we are identifying as man 1, man 2, woman 1, and woman 2. And really importantly, what we're going to do is we are going to flip coins. A coin is flipped. An outcome of tails is going to give them to the treatment group, and an outcome of heads is going to give them to the control group. And it's really important for each method, both the chip method, which we'll do in a moment, and this coin flip method, we're going to do them in the order of man 1, man 2, woman 1, woman 2, and this is going to make life a lot easier for us. If we didn't know that order, things would be a lot wackier. But luckily, we're fixing that. We're going to kind of sort of control that situation. And so if we want to look at this, arrangement A, you just want to notice, okay, what has to happen is that man 1 needs to go to the treatment and man 2 needs to go to the treatment, which means they both need to flip tails. So the first flip has to be tails, and then the second flip has to be tails, and then the crazy thing is you're done. Because there are already 2 people assigned to the treatment. The control group is going to get everyone else. In this case, that is woman 1 and woman 2. Of course, living in the binary with this problem, we'll just kind of lean into it and go for it. It's all made up anyway. And so we notice this. Tails, we know the probability of flipping tails on any one flip is a half. And so we're going to get the probability of tails is just 1/2 multiplied by 1/2. Of course, every coin flip is independent, and so we get a probability of 1/4. We're going to put that in right there. And we are going to do this a whole bunch more times. So B, has to be a man. Man 1 has to get treatment. Man 2 has to get control. And then woman 1 has to get treatment. So let's write that down. So B, man 1, we need to get treatment. That's tails. Man 2 would have to get control. That's heads. Woman 1 would have to get treatment, that's tails, and then we'd have 2 in treatment. Woman 2 would be automatically put into control, and so we get probability of tails, then heads, then tails is of course 1/2 times 1/2 times 1/2, which is 1/8. So that's 1/8. And C, let's do it all out. C, we have man 1 gets treatment, so tails. Man 2 gets control, that's heads. Woman 1 gets control, that's heads. I'm not going to write it out, but this is going to give us 1/8 because it's going to be 1/2 times 1/2 times 1/2. So there's 1/8. D, so we need man 1 to be in the control group, that's heads. Man 2 in control group as well, that's also heads, and then we're done. So that's the big difference from this one. If you get the same flip twice, then woman 1 and woman 2 are automatically in the other group. So this is going to be 1/4 again. E, man 1 has to be in control group, that's heads. Man 2 has to be in treatment. All right, so woman 1 could still go either way. She's got to be in control for it to be assigned arrangement E, and that's going to give us 1/8. Again, we don't have to write the last one in because we don't even flip. Woman 2 automatically gets put in whatever's left. And F, we could do this one a couple ways. We could add all these probabilities up and figure out what's left. And it's going to be 1/8 again, but just looking at they would have to be heads. Man 2 would then have to be treatment. Woman 1 would have to be treatment. So heads, tails wouldn't matter what happens after that. And so that would be 1/8. All right, fantastic. So we looked at this question for the sequential coin flip method. What is the probability that man 1 and man 2 are assigned to the same group? So we just want to look and see, all right, when does that happen? That happens here, arrangement A. That happens here, arrangement D. And it doesn't happen in any of the others. And so we go to those two probabilities, 1/4 and 1/4 again. And so it's actually 1/2. The probability is 1/2, which I think should be surprising. I think naturally we might think if this was like a really good arrangement, maybe it would be a third, maybe something, I don't know. But we see a half here. Okay, that's what we see, and that's what this ended up being. So let's go to the next page where we still have the same structure. We're still in terms of it's going to be man 1, man 2, woman 1, woman 2 in terms of selection order, but we're going to use this chip method where we have 2 chips marked treatment and 2 chips marked control. And so, of course, that means we have 4 chips, 2 of them say T, and 2 of them say C. So 2 for treatment, 2 for control. And this is going to be one of these things where we are selecting without replacement. And so what happens on that first chip draw is going to affect the probabilities of the second chip draw. Whatever the first 2 were are going to affect the probabilities of the third, and so on and so forth. And so if you've done enough of these problems in your life, which I have, and maybe if you happen to be a math competition kid who likes doing that, maybe you've seen these. You can kind of look at this and you have a feel for it. It's like, this is going to be all 1/6. All 6 of these are going to be equally likely. But we got to prove that. We got to show that that's actually the case, right? Because you can't rely on just your gut every single time, and sometimes it's wrong. And so we want to check these things out. And so if we look at option A here, we can see that what we need to happen is that man 1 needs to get the treatment, and then man 2 needs to get treatment as well. And so we think, all right, so the probability of essentially it being the order treatment, treatment, control, control, because, the woman 1 and woman 2 could still reach in, grab a chip will just be the control group after the 2 men have taken the treatment ones, but it would still happen. And we would say, okay, well, the probability of getting a treatment for the first man, for man 1, is 1/2, because it's 2 out of 4. But if he's taken that one, then the probability that man 2 gets treatment is only 1 out of 3, because there are only 3 chips left and only 1 of them is a treatment chip. The probability that woman 1 gets control is now just 2 out of 2, because there's 2 chips left, but they're both control. And 2 out of 2 here, we are going to multiply these together, and we're going to get 1/6. I'll ask you to check me that that's indeed correct. Or, check yourself, I guess. So probability of arrangement B is the probability that man 1 gets a treatment chip, man 2 gets a control chip, woman 1 gets a treatment chip, and woman 2 gets a control chip. It's so hard to say all of these things. But that's fine. So we can take a look at this, and I realized that the clock started over again, so this is 2 videos I meant to do as 1, whatever. Probability that man 1 gets a treatment chip is 1 out of 2. Now, the probability that man 2 gets a control in this situation where the first one has taken a treatment chip is actually 2 out of 3. Because there are 2 control chips remaining out of a total of 3 chips combined. Then, now there's 1 of each. The probability that woman 1 gets a treatment chip is 1/2. And then, of course, there's only 1 thing left, and so that's 1 out of 1. And we can look at these, do a little cross-canceling. You're going to get 1/6 again. I'm going to spare you all of this energy. You could do the same thing, and I assure you, you will get 1/6 across the board. So I'll write that in. You can check that on your own, but I don't want to make this video take forever. So we look here, this little question for the chip method, what is the probability that man 1 and man 2 are assigned to the same group? And we see, again, that's assignment A and assignment D, but now each of these only has a probability of 1/6, and so that is 1/3, because 1/6 plus 1/6 is equal to 1/3. Question C seems to come out of nowhere. 16 participants consisting of 10 students and 6 teachers, yada yada. You can read, you don't need me to read that out to you. But which method, the sequential coin flip or the chip method, should we use to assign treatments? And I think from this is we want to say the chip method, because we like things to be as, sort of evenly likely as possible. And so I would say the chip method because every arrangement is equally likely. As opposed to with the coin flip method, we saw that that is not the case. Every arrangement was equally likely. We're going to hope, be a little hard, it would just be onerous to prove it. It actually wouldn't be hard. It would just take forever to show that if you did some kind of comparable chip method, that this would work with 16 people, just like it worked with 4. And that's really all we got to do. So chip method because every arrangement is equally likely, as opposed to the coin flip method where some arrangements are more likely than others. Okay, with that, I hope that this made sense.